Welcome back to the deep dive. We're here again to explore another corner of the number universe for you, our number theory students. Today we're digging into OEIS sequence A000325. It's defined by a pretty neat formula. AN equals 2NN. Just give you a feel for it, the sequence kicks off like this. 1, 1, 2, 5, 12, 27, 58. So yeah, let's unpack this and see where it leads us.
Absolutely. That formula, AN equals 2NN, it looks simple, doesn't it? The OEIS actually lists its offset as 0, 3, so technically A0 is 1 and A1 is also 1. Those first two terms are the same. But the really interesting part, I think, isn't just the algebra. It's how this very direct formula shows up in, well, a whole bunch of combinatorial situations.
It's like a common thread. You called it a mathematical fingerprint before, which I like. So what are some of the first places we see this sequence appear? What makes it connect to so many counting problems?
Well, one of the maybe more surprising ones connects to card shuffling. It actually counts the number of distinct ways you can arrange deck event cards after just one single shuffle, like a standard riffle shuffle outcome.
One shuffle. That's surprisingly specific. Okay.
Yeah. And another fairly accessible one is counting subsets. It's the number of subsets you can form from a set of n items if you exclude all the subsets that contain only a single item.
Ah, so you take the total number of subsets, 2n, and you subtract the n single item subsets. 2n. Okay, that fits perfectly.
Exactly. So it starts linking basic set theory to this sequence.
So we've got cards, we've got subsets, pretty concrete stuff, but you hinted it goes deeper into more, let's say, abstract areas.
It certainly has. These initial examples are just the tip of the iceberg, really. For instance, in the study of permutations, A000325 counts the permutations of n items that have at most one fall.
A fall. What's a fall in a permutation?
Good question. A fall is simply when a number in the sequence is immediately followed by a smaller number. So like in 312, the drop from 3 to 1 is a fall. This sequence counts permutations with 0 or 1 such drops. These are sometimes called Grassmannian permutations.
Grassmannian. Right, that connects to algebraic geometry, doesn't it?
Precisely. It shows up there too. And it also appears in graph theory, specifically related to dict paths.
Okay, dict paths. Those grid paths that don't dip below the axis. How does 2n relate here?
It counts dict paths of a certain length, semi-length n, that have no more than one long ascent. It's another structural constraint that remarkably leads back to the same numbers.
Wow. Okay, so permutations, geometry, graph theory paths. And is there another way to generate these numbers? Maybe a recurrence?
Yes, there is. You can define it recursively. an plus 1 equals 2 times an plus n minus 1. You start with the a0 in 1. So a1 would be 2a0 plus 0, 1, which is 2 and 1, 1 is 1. And a2 is 2a1 plus 1, so 21 equals 2. Then a3 is 2a2 plus 2, 1 plus 1 plus 1 equals 5. It matches up. This recurrence gives us another perspective on its structure and how it grows.
That growth, 2nn, is dominated by the second term, so it grows exponentially. Fast. What about purely number-theoretic properties? Do the numbers themselves have interesting features, like divisibility?
Yes. That's actually quite a striking property. If you look at divisibility by primes, it turns out that for any prime number p, you can find infinitely many terms in this sequence, an, that are divisible by p.
Infinitely many. For every prime, that sounds unusual. Many sequences don't behave like that, right?
Exactly. It's quite profound. It means this sequence maintains a sort of universal relationship with prime numbers. No prime is avoided forever. It suggests something deep about the structure captured by 2n in it. It's not just combinatorial. It resonates through number theory itself.
Okay, so let's try to wrap our heads around this. We started with a simple formula, 2n, and we've seen it connect card shuffling, subsets, specific kinds of permutations, constrained paths on a grid, and now this universal prime divisibility.
It really is a testament to how fundamental mathematical structures can manifest in, well, quite unexpected ways across different fields.
So the takeaway here isn't just about A000325, but maybe about how these sequences act like bridges between mathematical ideas.
I think so. Yeah. It prompts you to consider, when you encounter a sequence like this arising from seemingly unrelated problems, what underlying principle does it point to? What other hidden connections might be lurking, waiting to be discovered by following these numerical fingerprints? It really opens up the idea of a deep, unexpected unity.
A great thought to end on. It certainly invites us and you listening to keep looking for those deeper connections. Thanks for joining us on this deep dive.